Hi, Physics 1 students. So we're going to take a minute and talk about torque. So this is kind of the second part of Chapter 10. First, we talked about rotational kinematics, and we motivated this as being in analogy to when we talked about kinematics way back in Chapter 2, and we can kind of motivate torque in the same way. So if you think back to when we talked about Newton's laws in Chapter 4, we know that the sum of the forces on an object is equal to its mass times acceleration. Well, now in Chapter 10, torque behaves similarly. So the sum of the torque on an object is going to equal something called the object's moment of inertia times its angular acceleration. Now, technically these quantities, torque and angular acceleration, are vectors as well, although we're not going to emphasize that as much because the definition for torque requires a little bit more sophisticated vector math than all of us have used so far. So we're going to kind of use a little bit simpler way of talking about it. So the technical and sort of most correct definition for torque would be that it's the cross product R and F. And we can also write this as, so I know some students have dealt with the cross product before by looking at the determinant of a matrix, but many of us haven't. So another way to think about this is that this is R F sine theta. And let me draw you a picture to kind of show you what I mean. But to step back a second, why we care about this is because torque is going to explain why things experience an angular acceleration, just like how force explained why things experience a linear acceleration. So this is an important idea for us to be able to explain where this angular acceleration that we talked about in the first part of the section of Chapter 10 comes from. So, all right, to flesh out a little bit more how to visualize torque, or here's one way to think about it. Imagine like a wrench. Suppose we have like a big wrench here that's turning a bolt or something. So it depends on two things. R, which is going to be, if I can draw a straight line here, the R would be how far to where you're going to push on this wrench with some force. Okay, so here's force, here's R. Now, and it depends on the angle between them. So if you think of the angle as being here, and notice this is going to be maximized when theta equals 90 degrees, i.e. when this is perpendicular. And I think this is probably familiar. You imagine pushing on a wrench. You know you're going to get the most oomph, you're going to get the most torque when you're pushing on it perpendicular to the handle of the wrench. So let me label these. And you can imagine making this angle smaller. You know, maybe you push like directly on the end of the wrench. Let's call this F3. F1, or sorry, torque 1 is going to be the largest because that would be RF sine theta when sine theta goes to 1. Torque 2, so let's assume that these forces, the magnitudes of these are all the same. So for F1 to F3. Torque 2 is going to be less than torque 1 because this RF sine theta, this sine theta is going to be less than 1 now because that angle is less than 90 degrees. And torque 3 is going to be equal to 0 because notice the force and the R are aligned. The angle between them is either 0 or 180 degrees depending on how you're thinking about it. And so this will equal 0 because this is 0. And this should agree with our intuition that if you push on the end of a wrench, it's not turning the bolt, it's just pushing the wrench into the bolt. All right, so that's torque. The other ingredient here that we need to understand this sort of analog, rotational analog to Newton's second law is I. So what is I? I is something called the moment of inertia. And the short story is that this is the rotational equivalent of mass. So it depends on the mass, but it also depends on the geometry. So for a quick example of this moment of inertia, imagine that you have a cylinder that you want to spin around its center versus like a piece of tube where all the mass is on the outside. And suppose they have the same mass. And they have the same radius here. This first example, this tube has the cylinder has a moment of inertia of 1/2 mr squared, while the tube would have a moment of inertia of mr squared. And the main reason that I'm showing you this is just that this is not the same as this. So I1 is not the same as I2. So not only does it depend on the mass, it depends on how it's organized. And kind of qualitatively, you can think of it as like with this tube example, the mass is on the outside. It's going to take more torque to accelerate that because the mass is further from the center, as opposed to the solid where some of it's in the center. It takes less torque to accelerate that, even though they have the same mass. Now, in general, you need to use integration to compute these moments of inertia. And so that's a little beyond what you're responsible for class. But the important takeaway with this is just to recognize that the moments of inertia are different for different objects, and that it contains both information about the mass but also information about how it's arranged. So now we have kind of all the ingredients that we need to look at torque problems. So let's look at a couple torque-related problems. Oh, and I would mention too, with regards to these moments of inertia, there's a chart in your book. See chart 10-20. Here, I can actually, let me paste it in here and it'll give you a flavor for what I'm talking about. So it looks like this, and it gives you kind of the moments of inertia for different shapes, so for spheres and cylinders and everything. And notice, these are, a lot of them are very symmetrical objects, and that reflects the fact that those have simple moments of inertia. And it gets at this fact that, in general, if you wanted to calculate it for a weird shaped object, you would have to, you'd have to use an integral, and it would have a complicated formula for its moment of inertia. All right, so let's look at a couple example problems on this, just to practice. And these are the ones that we talked about in class. Different sections talked about kind of a different mix. But the first question here says that we're having a person riding a bike. And so let's draw kind of a little cartoon here of what we're talking about. Imagine oh wow, that's not a very good gear. Imagine the gear on the bicycle, and we have the crank arms on the bicycle and the pedals. And the question is, what is going to be the maximum torque that the person exerts on the bicycle crank? And hopefully this is a good example because it kind of gives you a system that we can kind of visualize and that we're familiar with, riding bikes and whatnot. So the first part of the question, what's the maximum torque? So we imagine, the weight is pushing, the person's weight is pushing down on the pedals. And this R, think of the R as being from here to here, the radius of the crank. And you can see that that angle, the angle between them, call that theta, is going to be maximized when this is, of course, sideways or flat, because then you have, the weight is pointing straight down and r from there to there. And so then in this case, that would be perpendicular, and your RF sine theta becomes just RF. And we can put our numbers in here, and we would find that this would be, 0.16 meters times the mass of 57 kilograms times 9.8. And we multiply this together, and we would find that this is, 89 Newton meters. Now, one quick note. This may seem weird that this has the same units, or it's composed of the same units as energy, but this is different. And I think that probably the best justification for this is that recognize that this is a vector quantity, the torque. And so just keep this kind of in your mind as a separate entity from energy. And if it helps, you could write this as meters times newtons to emphasize this notion of its being a length times a force. So it's a force at a length to help us kind of distinguish these. So that would be the maximum torque. And then the second part of the question is asking us, qualitatively, how could we increase the torque? Well, there's a number of things you could do. You could gain weight. That would increase the torque. You could use a longer crank arm, increase R, in other words. So just to clarify, remember R is from here to here. R. You could pull down on, on the other, or on the handlebars, and maybe exert a force larger than your weight. You could, pull up with your other foot. Like recall, fancy bicycles, your feet actually attach to the pedals, so you could pull up on the other side, and that would increase the total torque. You could, and practically how this is done in a bicycle is you use gears. So that's a little bit beyond what we're talking about, but mainly just to have in mind that there's a lot of things that you could do to modify the total torque. Increase the length, increase the force in different ways. All right. So the second question, example question that we talked about in class is one that involves that asks us to use this idea of moment of inertia. So it gives us a little bit of exposure to this idea, which I think is good. So we have a solid sphere. So imagine we have a sphere, and we're going to spin up the sphere, and we know the torque, and it's going to accelerate it uniformly from rest through a total of 180 revolutions in 16 seconds. And what we are looking for is what is the mass of the sphere. So the torque in general is equal to the moment of inertia times the angular acceleration. We have information that we can use to get the angular acceleration. We can look up what the moment of inertia for a sphere is. We're given the torque, so we can find the mass by putting in the things that we know and then solving for the mass. So the first thing is, if we look up the moment of inertia for a sphere, it's actually up here in our chart. We can see that it's equal to 2/5 mr squared. So we'll make use of that, where r is the radius of the sphere. And notice the mass is inside the moment of inertia. And the other thing that we need is we need alpha. So we can get alpha, the angular acceleration, from our rotational kinematics. So notice we have this thing, it spins through a number of revolutions in some amount of time. So recall we have an expression theta total amount of angle that it goes through is going to be equal to the initial angular velocity times time plus 1/2 alpha t squared. Now, there isn't any initial angular velocity because it's starting from rest. And so we can just solve this for alpha and make sure that we have things in the right units. So this would be theta, let's see here, 2 theta over t squared. Now, the total amount of angle would be 180 revolutions times 2 pi, because there's 2 pi of angle per revolution, and then divided by our time squared. And when we crunch those numbers, we would find that the alpha is about 8.8 radians per second squared. So we have alpha, we have our expression for the moment of inertia for the sphere, we know what the torque is. Let's put these ingredients together and solve for the mass. So this will be 2/5 mr squared. We can solve for m. In terms of this stuff, it will be 5/2 times the torque over r squared over alpha. And let's put our numbers in here. So 5/2 times the torque was 12. And the radius was half of 0.65, so I'll just put 0.65 over 2. That thing squared. And then the alpha we calculated just now was 8.8. So if we put in our numerical values and crunch the numbers, we would find that this would give us a mass of about 32 kilograms. And so you can see that with this rotational situation, rotational dynamics, it's a little bit more complicated because we have, it depends on the mass, but the mass is inside this quantity, the moment of inertia. So I would point you to these charts to look up the moment of inertia as you're working on, on homework. And I would say, I'm not going to ask you to do like an integral to find a moment of inertia. But I suspect that that's going to be something that you'll run into in one of your later courses where you look at dynamics.